Okay, we're going. It's on. How you doing, Emily?
Cool. Doing good. How are you?
Doing good. Thanks for being here. Appreciate you taking the time to talk to me and share some stories and astronomy info.
Yeah, definitely.
Yeah, and well, first of all, congrats on the book too. Loved it. I read it. It was great. I wish I had it. I got the ebook version. There we go.
There we go.
It looks great. Yeah,
I never miss a chance to show off the cover art. So the fun part about the cover art is you can see this beautiful little drawing of the galaxy, and then if you take off the jacket, you get this wonderful star print on the inside. Yeah,
that's
so. If you want a really pretty book to give somebody, then they can play with the cover art of this. Yeah,
that's good.
I wish I could take credit for it, but it was the wonderful artists at the publisher.
Right. That's awesome. I'm a little bummed because I just got the ebook. I'm bummed. I wish I got that because I always take the jackets off, and that's the best like hardcover book under a jacket ever.
I'm a big ebook person, though. It's just so convenient because I can read the books on my phone or anywhere. So I get it.
Yeah, that's true. Well, yeah. I mean, so I was excited to read your book, and I'm glad like I found it. I'm glad I found you because I've been into kind of astronomy, and like I had the Griffith Observatory, the I don't know who he is, what his name is, but the head honcho at the Griffith Observatory on the show. And so we got to talk about all that stuff, and it was super fun. And I've never even looked through like a big telescope like that, just kind of like little, hobby guys who have been sharing their kind of stuff. And it's awesome. I love it. But I'm always wondering like okay, for me, that was awesome to look through that, right? Like I loved it. It's so cool. But I'm like, how does an astronomer, what do they do? Do they see something that I don't see? Am I missing something? Like, what is going on? Are they just looking at stuff and they know stuff? So that's why I was excited to get into your book, because that was always a question I had.
Yeah, it's something that I get asked a lot when I tell somebody like on an airplane that I'm an astronomer, because it's something that you don't always realize when you're embedded in a field, but there's very few professional astronomers in the world. There's about 50,000 of us on the planet. And most people have no idea what we do, but they're curious about it because it's the sort of like romantic, we study the universe and we explain how the universe works. And somebody will usually say, oh, that's really cool. But like, how are you awake right now? Shouldn't you be nocturnal? Like, don't you just look through a telescope all night, every night? Or do you have a telescope in your backyard? And then when I tell them I live in Seattle, there's this moment of, that doesn't sound good for astronomy. Or they ask if I get to go to telescopes like Hubble, which is in orbit, which we don't get to do, unfortunately. You don't get to become an astronaut to go observe with Hubble. So there's a lot of questions about how we do like just the nuts and bolts of our job and what our life is like.
Mm-hmm. Yeah, no, and that's the fun part. I love that you share all that stuff. And like one of the big things that was like kind of mind blowing to me is like you guys don't even really look through a telescope anymore. There's not really eyepieces very often that are used, right?
Right. So we want to capture data from usually things that are very, very faint and far away. So if you're doing the equivalent of taking a photo with the camera, it would be a photo where the shutter of the camera is left open for minutes or hours, sometimes at a time. So we need to take exposures like that, save the data nowadays digitally, and then we study it later. So some of the big telescopes in the world, we actually don't even have eyepieces for. We just have really amazing cutting edge cameras or scientific instruments that we put on the back that can capture the light from those stars or galaxies or whatever we're studying in different specific ways, so we can then go off and analyze it later. But it means that we tend to look at what we're observing on a computer screen rather than directly through the telescope.
Right, I see. I mean, it makes sense. Of course, that's what it is today. But so that means that even if you were to put an eyepiece on there and try to look at, a distant star or whatever you're looking at, you may not even be able to see it because your eye can't capture enough light or something?
Sometimes, yeah. I mean, if you put an eyepiece on a giant telescope, what you see is absolutely spectacular, but it doesn't compare to what you would see if you took a camera and just left it open for hours and really got to capture like every last little crumb of light coming at you, because it just makes dimmer things more visible. But that's part of the sort of art and sometimes the challenge of professional observing.
Right. Yeah. Okay. I get that. So my mom got that new iPhone where you can do like a long, exposure on it. And so we were doing some stuff. We were up in Moab in Utah and taking some photos of stuff.
Yeah.
and trying out like her new camera, and we would take a photo, and then like the sky looked awesome, the stars were amazing, that iPhone camera is crazy, but we would look at it and you could see the sky like we were seeing it, but then you'd zoom in and it was almost like there was more stars like as we zoomed in. Is that the same thing where it's just letting in more light than we could kind of really see with just our eye?
I don't know exactly how the iPhone camera winds up storing or capturing long exposures like that, although I've totally done the same thing with my phone. But there is very much that idea that the longer you expose, the dimmer an object you can see, because you're giving photons, so little bits of light, just more and more time to build up on an image, and more time to sort of create something that you can actually see.
Okay. That makes sense. Yeah, it's so cool. It's mind blowing.
Yeah.
So because you talk about, you mentioned it, and then you mentioned it in your book a lot too. It's like oh, sorry, that was my dog.
No worries.
You mentioned that like you'll look through a telescope will give you like data. What is that? What is the data? What does that mean? Is it just an image?
So sometimes it's just an image. There's really two fundamental types of data in astronomy, and one is a picture, basically, so imaging data. And this is when you have a fairly straightforward camera on the back of a telescope, an amazing camera, but the kind of camera that you and I might picture. And it saves a digital image of a galaxy or fields of stars or whatever it is that you're studying, and then you analyze that image later. The other type of data is something called spectroscopy. And what that is splitting up light into its spectrum, which is a term a lot of people have probably heard, but may not have heard scientifically. And the idea here is that you grab light and sort it out according to its color. So a detector that takes a spectrum will let light in and then say, put the very bluest light over here, and then the greenish light here, and then the yellowish light here, and then the red light here, and split it into individual colors. And the reason that that's so valuable is because we can learn a lot about the sort of underlying physics going on in an object by studying light like this. There are atoms that'll have very telltale signatures. They'll emit or absorb light at a really specific color. So like nitrogen will give you this sort of glowing red light. There's hydrogen that will give you a bit of glowing light in at a reddish orange color, and then another bit of light in a very bluish purpley color. You'll see a little trio of bright spikes from calcium that's very dark red. And if you can piece all of this together, you can kind of look at the chemical fingerprint of whatever it is that you're studying. So you can look at a star and say, oh, I know how much iron or titanium or hydrogen this star has. And that tells me something about what's happening to this star, where it is in its lifetime, what's going on in the physics of its outer layers. And we can pull a ton of information about a incredibly far away object out of just sorting out the light like that. So that's the kind of data that I take a lot. It looks super boring because when you take a picture of light and then just sort it out by color, what you wind up with is this squiggly line saying, well, there's a little blue light here and then a lot of yellow light and then a little red light. And it doesn't look like those gorgeous Hubble pictures that we're used to seeing, but there's a lot of scientific power in the squiggly line. So right. It's all just what kind of questions you're trying to answer.
Right. No, that makes sense. And then, so when you're saying that like, nitrogen emits a certain color or something, is it a visible color, or is it like a how does it?
Sometimes it is. So we actually have telescopes that can capture all sorts of wavelengths. So basically the complete range of the electromagnetic spectrum. Yeah. And the kind of light that our eyes can actually detect and see is a pretty narrow range of color. Right. So stars actually will emit or absorb light in the same wavelengths that we see with our eyes, but they also might emit ultraviolet light, or we might see signs of them in the infrared, which is past the wavelength that our eyes can see. We'll study some stars in X-ray light, or we see gamma rays coming from some objects, or we'll study radio wavelength light, which is really long wavelength light. And we've designed telescopes that can do all of these things. So it depends again on the scientific question that you're trying to answer.
Right. Yeah, that makes sense. That's always something I need to remind myself of, sort of, and I always look up a graph of the different, wavelengths, I guess, because it just seems confusing and unintuitive to me that radio waves are basically light. It's the same type of thing as a visible light, but it's just a different wavelength, right?
Yeah, it's a different, if people are used to radio meaning, something you listen to, and the radio in your car takes radio wavelength light and is able to sort of translate it into something that you can hear. But radio, yeah, it's just a wavelength like what we see with our eyes. It's just too long for our eyes to detect.
Right. Okay. And then, so how are you, do you know that like blue means nitrogen or whatever it is? Like, how is that kind of stuff determined?
So that actually goes back to atomic physics. And if anybody remembers learning about atoms in school, where you think about, an atom has a little nucleus that's got protons and neutrons in it, and then electrons kind of zipping around it. From our physical model of an atom and from what we know about how atoms work, we can figure out exactly what color light different atoms will emit or absorb when we see them in, say, the gas and the outer layers of a star. So it all just comes back to the physics and math of how the universe works. But it's kind of cool how it sometimes turns into, look for this blue light from this star or something like that.
Right. Okay, man, that's cool. So it's like stuff that, I guess it's almost like, is it a different field?
Sometimes, this is one of the fun things about astronomy is we are a wonderful mashup of different sciences that we use a ton of math. We use a heap of physics, but then it gets really deep into chemistry. There's a subfield called astrobiology, which sounds made up, but it's actually a really fascinating field. We are becoming more and more dependent on computer science and really advanced computer science in some ways to work with the data and the sort of physics models that we use, but it's a mashup of different fields. So the people that originally did research on the atom may not have done it with astronomy in mind, but we now use it all the time in what we do.
Right. Yeah. No, that's so cool. That makes sense how that they like influence each other and kind of bounce off each other like that. So how do you because I'll get behind a telescope and want to look at a planet or something, that just looks cool to me. How do you kind of decide what you want to do or focus on or what you're looking for? Is it just kind of what interests you? Is there like a guidebook? How does that work?
So it starts out with what interests you, but it's actually really difficult to get time on a telescope. So a world-class telescope is a really precious resource, and we have to submit an application to use it the way that other scientists submit applications for grant money. So we make a plan ahead of time. My research specialty is I study how stars kind of evolve and then die, and how they make something like a supernova and then leave behind something like a black hole. So I might write a proposal saying, I want to study this type of star. And I'll do the research and say, I want to study 74 of this type of star that are visible in October or November or December. And I want to use this telescope with this spectrograph on the back of it for 2 nights to do that. And you plan out the whole night almost before it happens. And then you submit a proposal saying, do you think the science is worth that time? And a panel of other scientists will look at it and say, maybe no, but if you're lucky, yes, we think you do. And we've decided that you will have November 20th and 21st as your dates on the telescope. And then you make a very detailed plan for those 2 nights, saying exactly which stars you want to point to. And this is all designed based on the scientific question you want to answer. And the worst part is if you show up on the night of November 20th and it's pouring rain and you can't open the telescope, you're just done. You don't get to stay an extra night and hope you've made up the time because somebody else competed and was given November 22nd and will be coming with their own program. So It makes the time really precious, and it makes it a little tense. You're kind of nervous while you're observing at a telescope, hoping that you use every minute of time.
Yeah, I could imagine there's some anxiety there.
Yeah.
Yeah, right.
You're really worried about breaking something or doing something wrong.
Right. Yeah, I can imagine this massive telescope. That was something too that kind of blew me away reading the book, is how precious the telescope time was. Because I don't know, I had just assumed that every astronomer has a big old telescope, I guess. I just never thought about it, but it does make sense that there's a limited amount of telescopes and it has to be shared between all the astronomers.
Yeah, these are really world-class scientific facilities, and we have to build them out in the middle of nowhere. Building a really top-notch telescope is a massive endeavor. So we unfortunately don't have one telescope per astronomer. That would be amazing. But as is, we need to really make careful use of the resources that we have, which means that we're all applying for telescopes and we're all sort of sharing the time. Sometimes telescopes will take data that will become public after a certain amount of time, so we can then share each other's data. And we have to be able to collaborate and share the resources. But we are working with a world in which we unfortunately don't have that many world-class telescopes to operate with. It would be amazing if we had more. So yeah.
So how many nights, like a year, do you get on a telescope typically?
I can tell you how many nights I get. It varies from person to person, but I'll have maybe half a dozen,
For the whole
5
year?
to 10 in a whole year. And
Wow.
I'm counting at this point, I have research students who work with telescopes too, but maybe I could see a year where I have as little as 4 or 5 nights, and then a year when I might have as many as 10 or 20, but that'll be, for me, the high end. I have other colleagues that do different types of research where they just need more individual time at telescopes. So they might have 30 or 40, but it's still not that many. We spend most of our time not at telescopes and most time working with the data that we got. One night of observing can fuel months of science sometimes.
Yeah. Oh man, that's crazy. So most of your time is spent kind of just analyzing the data that you got that one night.
Yeah, most of my time is spent right here at my laptop working with the data that we got from the telescope. Yep.
Wow, that's crazy. Yeah, I feel like that's such a misconception people have. We would think you're at a telescope all the time.
Well, and going to these telescopes is an incredible adventure on its own because they're out in the absolute middle of nowhere. You're really undergoing quite a travel odyssey to get to them. And some of the things that we'll do to get to these telescopes and to make these telescopes work can be pretty extreme. But it's an interesting combination of going to the absolute ends of the earth to use these telescopes. And then you go back and sit in your office and work on the data. And you're unraveling things like what dark matter is, or how stars die, or how black holes work, just on your laptop using the data that you got in a telescope in the middle of nowhere. So it's a fun combination of contrasts for a job.
Mm-hmm. Yeah. Are you ever mad at yourself for missing like a photo or a piece of data or something that you needed to get one night?
You usually know when you've missed something. If you have
Okay.
a list of objects and say there's a cloud right where you want to observe, sometimes you know that it's lost. Other times you may go to the data and say, oh, I wish I had pointed at this thing for 15 minutes instead of 10 minutes. I might have gotten a better view. But it's also, you don't want to have those kind of regrets because the only thing worse than not getting a night of time on a telescope is wasting a night of time because it's so precious.
Yeah.
So I will look at the data as it comes in real time, and I'll try to crunch it. And if I think I need 5 more minutes pointed at something, I'll go get it right then, because if you are regretting that 3 months later, it's too late. The science is lost, probably forever, because you can't just go back and say, hey, I screwed up. Do you want to give me another night of time and hope I don't make a mistake? So it's really a lot of practice and preparation goes into really getting it right the first time.
Right. Yeah. Yeah. You spend a ton of time like preparing your schedule for the night, basically, right?
Oh, yeah. Yep. Mm-hmm.
Yeah, I can imagine it. God, when you have that little amount per year, that small amount of nights, I can imagine the anxiety. So let's talk about visiting, like what it's like to go to an observatory, because you mentioned that they're in like super remote areas. What does that mean? Is it just in the middle of the desert? Are they up high on a mountain? What are we looking at?
So both of those things. We like to build telescopes in places that are very high and dry because it means that the air and weather quality is going to be really good. You want places that have good weather, so you're not going to lose nights to it raining or snowing or something like that. And you want an atmosphere that's very nice and still, because if the stars aren't twinkling very much, it means you're going to get a nice sharp picture of them. We also like building these in locations that are obviously very dark. If you built an observatory in New York City, you'd be a little disappointed because there's so many city lights putting light pollution into the sky and really wrecking what you might see. So some of the best sites in the world for astronomy are places like the desert in Arizona or Chile or the tops of mountains in Hawaii, places where you can really get away from city lights and really get to spots where the atmosphere is wonderfully, perfectly still and you can get the best images you possibly can. But sometimes getting out to these observatories is a whole adventure on its own, because you'll land at the big airport, fly to the small airport, fly to the smaller airport, drive for 3 hours, like that kind of thing.
Yeah. Because some of these places, they're so like strict on the, it's got to be dark around there and everything, that they'll make you turn your headlights off in your car when you're driving there, right?
Yep. I've passed signs on the way up to multiple observatories saying no headlights after dark. And you're usually driving there during the day so that you have time to, get rest and get sleep. Because when you're observing, you are, when you're taking the kind of data that we see with our eyes, at least, you're on a nocturnal schedule. So you do shift to sleeping while it's light out. But yeah, these aren't always the most developed or the most well-traveled roads too. So I have plenty of colleagues that have told me stories of some sort of car mishap going up or down this sort of bumpy mountain road when you can barely see and stuff like that.
Right. Yeah. It's just so funny to picture a sign telling you to turn your headlights off. That's hilarious to me. Mm-hmm. And then you mentioned that you want like a place with a still atmosphere. What does that mean?
So there's a term in astronomy that we use called seeing, and it's basically it sounds like a made-up word, but it's a scientific term for how much blur you're getting from the atmosphere. You've probably seen an example of this if you've ever looked at pavement on a hot summer day and seen the sort of shimmering heat waves coming off the ground, right, blurring everything. Our atmosphere will do that to a certain extent to the light coming to us through the atmosphere. So if the atmosphere is moving around a little, it'll blur or mess with the light that we're getting. And when you see stars twinkling in the night sky, you're seeing an example of seeing. So we want places where the atmospheric turbulence is very small, very minimal, so that the pictures that we're taking of the stars are wonderfully, perfectly sharp. And you can do that if you're in a nice, high, dry, cold place where you're not going to get very much atmospheric turbulence. And even then, from night to night, it'll vary. We'll measure the seeing during a night, usually multiple times, so that we can actually say, oh, the atmosphere is giving us this much blur or this much blur, or very little. It's a really good night. But it's a really important aspect of astronomy because it affects the quality of the pictures that we take.
Right. Yeah. So what are some of the other things that can affect or kind of make a night of observing go wrong, like the weather or, clouds or whatever it may be, I guess?
So there's plenty of things that can go wrong with weather. We can't observe when it's, say, raining or snowing because the giant perfect mirrors that we use in telescopes need to be kept really pristine. And you don't want water pouring onto those mirrors or freezing or anything like that. We'll also sometimes close when it's really windy because you worry about wind blowing in sand and damaging the mirror. And I tell a story in the book about sitting in a telescope on a perfect night. The sky was so clear, it was gorgeous. And the wind was blasting at 40 miles an hour, and we were just sitting there all night, so angry that we couldn't observe, but it wasn't safe to open the telescope. You also worry about things like the telescope breaking. These are enormous building-sized scientific instruments, but they're incredibly precisely engineered. So if a shutter breaks on a camera, or if a cable snaps, or if there's any small problem, it can completely take out the telescope for the night. And if that's your night, you're just out of luck. So there's a lot of things. I've had colleagues who've had observing runs disrupted by earthquakes because the entire building has been shaken to the point where they need to shut down and do safety tests. So there's a lot that can potentially go wrong.
Right. Yeah. Oh man, it's got to be so crushingly disappointing to go travel to this place, get the time and everything, go there, and then you can't even do it because it's just too windy.
Yep. I had it happen to me twice where I flew all the way to Chile and got to a telescope and sat in the telescope all night for 2 nights. And we never even opened the dome of the telescope. We never even came close to observing, but you had to stay the whole time. 3 a.m. on the second night, I'm going, we could still open. If it stops being windy, we could at least get a little data, but it's not the most fun part of the job.
Right.
Waiting out bad weather. It can get discouraging.
Yeah, I can imagine. And so what is it like? Cause are you staying the night at, or you're sleeping at these observatories, right?
Yeah, observatories like this will have dedicated dormitory facilities. They'll have kitchen facilities. So observatories also have a whole staff of people who are working to keep it running. There's engineers, there's people working in the cafeteria, there's cleaning staff making sure that we're staying, clean and comfortable while we're there. And it's really a multi-person operation to get even, 1 night of data at a telescope, and being able to stay in dormitories and being able to eat at our weird odd times. A tradition at observatories is that you'll have night lunch that you bring up to the telescope with you because you're probably waking up at about noon, and you have breakfast at 1 p.m. or so. You have dinner around 6 or so, and then you go to the telescope, and then you eat your night lunch, your last meal of the day around midnight, because the kitchen has kindly packed you a sandwich or something. Right. So you really are living on the mountain and living in this sort of nocturnal timeline the whole time that you're there.
Yeah, that sounds kind of like seems almost like a fun, nice job to be one of the staff working at the observatory like that. I feel like I could get into that.
I interviewed, so another funny thing that people don't realize about astronomers is they don't let somebody like me actually run and operate this building-sized telescope. They're extremely complicated instruments, and there are people whose job is to operate the telescopes. They're the telescope operators, and they're very distinct from the astronomers. So I'll go to a telescope and be working with the telescope operator, and I'll explain something like, I want to point to this object over there, and he'll be the one who actually sends the commands to move the telescope and keeps an eye on the health of the telescope as it's moving. There's the worry, like, you don't want a cable to get wrapped the wrong way. You don't want something to be moving or scraping the wrong way the whole time through the move. He's keeping an eye on a bunch of different systems in the telescope to make sure everything's working well. And they will work on the mountain for days and days at a time. They'll work a long shift and then go down and have a few days of normal and then come back up and do the same thing again. And there's similar shifts for all the other staff on the mountain. And there are sometimes support astronomers who will be full-time at some observatories to work with visiting astronomers that are getting their data. So some people really do take on the full-time life of working in an observatory, which sounds wonderful. But surprisingly, there isn't always a lot of overlap with that job and what people picture as an astronomer's job, which is sort of answering the mysteries of the universe, because there's so many more jobs tangled up in this idea.
Right. Yeah. No, I can imagine that. So what's the accommodations and food like? Is it pretty plush, or is it kind of like roughing it camping style?
Yeah, plush wouldn't really be the word. It's a little more, I'd call it pleasantly bare bones. Okay. There is a comfortable, clean bed. There's a shower, which is already super luxurious if you're used to camping. There will be cafeteria food that is wonderfully delicious, but pretty straightforward. There's one observatory that I love going to in Chile that famously has empanada day that everybody looks forward to all week, because they'll make these just like heaps of delicious empanadas that you can, if you ask real nicely, they'll sneak one into your night lunch bag for you. But yeah, it's pretty straightforward. You usually go with a backpack of clothes and warm clothes usually, because you're usually up in mountains where it can get pretty cold. I learned how to light a pilot furnace at one of these observatories because there was heat in the room, but you had to get under there and with a match and turn it on. So it's pretty bare bones, but it's really all you need. It's enough to keep somebody, rested and fed and safe and ready to do their science. Right.
Sure. Yeah. It sounds so fun. I'd love to. Do they ever let just non-smart people up there, just us regular dummies?
So there are some observatories that will give tours, but the tours are usually during the day, because at night it's almost always a working observatory. Usually if it is dark and clear out, an observatory is going to be working. They'll take a few nights off during the year to do things like engineering updates, but for the most part, that's when the place is actually at work. So you can go on a tour of something like Kitt Peak Observatory in Arizona or Mauna Kea Observatory in Hawaii. You can get to parts of these observatories during the day. But it's hard to get up there at night if you're not an astronomer. I didn't get to go to one for the first time until I was working in a professional capacity. I was a student and still learning. Actually, I write about the very first observing run I went on in the Last Stargazers, but that was the first time I'd gotten to go to an observatory.
Mm-hmm. Well, it makes sense because the time is so precious. They're not just gonna give it away. But they're
also very hard to stop by too. Like these aren't really on the way to places because they're so out in the middle of nowhere. Yeah,
that's very true. But that's too why Griffith Observatory is so special, is because it's for the regular, anybody can go and look through the telescope for free even too. It's awesome.
Yeah.
So it's cool that exists. So
definitely.
Can we talk? Because what was so fun about your book too is you talk about kind of the history a bit of astronomy and what it used to be like. Where now it's kind of it's all digital and taking photos and stuff like that. And even a lot of it's even remote. But can you just kind of share a bit of what it used to be, kind of with the big glass plates or some of that kind of stuff?
Yes. this is great. I have one actually on my desk that I can show people. So I was describing the way that we take data now with telescopes, where we tend to store it digitally. But pre-digital, the way that astronomical data was often stored was on sheets of glass like this. Wow. So you can only sort of see it in here. This is a plate that got a little bit overexposed, but it means that I have, let me see if I can get it up there. You can sort of see, you would basically take a glass plate like this that was specially treated to darken when it got exposed to light. And what would happen is you would order these plates from a company like Kodak, and they would come with these special emulsions on one side so that when light hit it, it would start to change color and darken. And if you stuck something like this into a camera and then opened the shutter, you'd slowly get this little color negative image of a star or a galaxy or whatever it is you were studying just on the plate. But these were so hard to work with because they would come pre-ordered from Kodak. They're not custom sized for your telescope or your camera. So you would usually have to slice the plate down to something like this exact shape. Some of them would be tiny little plates, and you would always have to cut them yourself. People figured out all sorts of chemical tricks, like baking the plates or freezing them or dousing them with ammonia. One guy swore by lemon juice. There was a lab that used hydrogen gas for a little while to treat the plates because you wanted them to respond to light as quickly as possible. And these were all ways to sort of speed up the reaction of the plate when light hit it. You'd then have to get into the telescope and load the plate into the camera. And sometimes the camera's bay for the plate was a little bent, so you'd take this plate and be like, and like try to bend it without snapping it. And I know people who had a plate shatter in their hands, or worse, they'd get it into the camera, start observing, and then hear this crack from inside the camera. And you just be doing all this work to get ready to take an observation. Then when you did the observing, you couldn't just, go into another room and like, boop, hit a button and let the telescope move. You had to sit with the telescope all night and ride along with the camera, sometimes hanging really high over the ground in the telescope and taking plates in and out and opening the shutter as the telescope operator moved the telescope to everywhere that you wanted to look. And then at the end of all of this, you take the plate back out, you go back to a dark room and you develop the plate. And then you get to find out if your observations are any good. And you're doing all of this in the dark, because remember, if you expose this to light, it darkens. So people had all these stories of like slicing plates in the dark, of cutting themselves trying to do this, and of like shivering on top of telescopes for hours while they were trying to take these exposures. So it was a really, really physical job back in the day. And it seems like this like kind of goofy, silly way of taking data, but we discovered astonishing things using plates like that. Edwin Hubble, the person that the Hubble Space Telescope is named after, discovered that there were other galaxies beyond our own, and discovered the fact that the universe was expanding, like these fundamental discoveries changing our picture of what the universe was like using this. So there was a lot of scientific power in it, but it was such a funny and fiddly way to observe.
Right. Yeah. No, that's crazy. We're in like a fun position where we can like talk about it and like hear all the stories and stuff, but we don't really have to do like that kind of crap work,
What's funny is you hear these stories and you think of like guys with pipes and suits and like, Victorian times. And we were using photographic plates up until the 80s. Like these happened basically until digital imaging technology got good enough that we were using it in telescopes. And a number of people that I interviewed for the Last Stargazers, I talked to more than 100 of my colleagues for the book. And a number of the people that I talked to had observed with plates and were telling me firsthand stories of what it was like to sit in a telescope all night, to slice these plates by hand. Whenever anybody talked about that, they do it with their eyes closed because they could remember just doing it in a dark room.
Right.
And I don't think I talked to a single person that was like, you know what, I want to go back and observe like that, because the digital data quality is so good and the science that we can do is so amazing and so efficient. But all of those people, their favorite story of observing or their favorite memory of observing was from one of those nights when they were sitting in the middle of a dome in the dark, perched next to the telescope with this like raft of glass plates that they wanted to use. So it was a wonderfully memorable adventure for them to have had.
Right. Yeah, it makes for better stories. That's for sure. Were they back like using the glass plates? Were they able to use different types of things to get like different wavelengths like you do now?
Yeah, there were different emulsions, so different chemicals basically that you could put on the plate that would be really sensitive to blue light or to red light or even to infrared light. Somebody told me a funny story about the infrared light because the plates would typically ship in big plywood boxes, and that worked great at keeping the plates inside in the dark, until you got to something like infrared light, because infrared light would pass right through the cardboard. So they had to, or the plywood. So they had to think of a different way to store it. But it all depended on what chemical treatment you had. A funny detail about them was that when you loaded a plate like this into a camera, there was the sort of side that was going to react to light where the emulsion was actually placed. And then there was just sort of the back of the glass. And you wanted to load it in with the correct side facing out. And in the dark, not being able to see the plate, you can't necessarily tell that it's emulsified. And astronomers figured out this trick that they would tap the plate to their lip to see which side was slightly sticky and which side had this chemical emulsion. This is like silver halide and like totally stuff you shouldn't lick. But they would do this little tap just to see if it was there. And I talked to people that swore they could taste the difference between like, oh, this is a blue plate, this is a red plate, or something like that. I can't imagine any of this was healthy. But you'll look at developed plates occasionally and you see like a little bit of a lip print or a little bit of a thumbprint from somebody that was just checking to make sure it was pointed the right way.
Right. So what would they, because when did like plates like that start to come into use? Like what did they have something before that even?
I mean, these glass plates were in use back in the I know for sure by the mid to late 1800s. I think before photography was a thing, really old school beginning photography, people were drawing. And you had things like a sketch in a notebook based on what you were seeing at that point, looking directly through an eyepiece. But these pretty much came into being as soon as we had photographic plate technology, and then they worked really well for decades and decades.
Yeah, man, that's so cool. So I want to get into some of your your stories that you have. So I guess can we talk about the very large array in New Mexico? Because you were a tour guide there.
Yeah. So anybody that's ever seen the movie Contact knows the Very Large Array. So this is this beautiful big array of radio telescopes in a very remote corner of New Mexico. And when you look at a radio telescope, it sometimes looks a little weird. It looks more like, the TV satellite that you put on your house, or it looks like a communications antenna, because it doesn't at a glance look like the little telescopes that you look through with your eyes in the backyard. But the concept is still the same, because you have something like a big dish that will collect light that comes down onto it and then focus it into some kind of camera. A radio telescope is just a really big dish that is designed to focus very long wavelength light into whatever detector or receiver it might have. So that array of telescopes in New Mexico is an array of 27 individual dishes that are all designed to work together. And I got to work there for a summer when I was I think between my junior and senior year of college. And it was my first time using radio telescopes, and I was just mind blown at how different they were from the telescopes that I'd used before that used the kind of light that we can see. The physics of working at such long wavelengths is totally different. Like I just said, the telescopes look really different, but it was so cool to actually get to learn how they worked. And one of the things that blew my mind was the idea that radio telescopes can observe during the day. We don't typically operate optical light telescopes in the middle of the day because the sun is really the only thing you can see, and it's going to overwhelm the light of any stars that happen to be in the sky right now. But a radio telescope doesn't have that problem. So I remember walking through this forest of radio telescopes, chatting with somebody who mentioned, oh, right now we're observing so-and-so, and we're just about to turn to, and just going, they're observing right now. I'm standing in the middle of working telescopes, and then you hear them all just kind of go and start to turn. It was really cool.
So, and then how does that work because you say they all work together, how does that work? Can you help explain it to a dingus like me?
It's actually, I remember taking a class for that entire summer on the science of how you get telescopes to work together. It's a process called interferometry, and it's a lengthy term for saying that we use light gathered at multiple points and basically keep careful track of the distance between those points to try and assemble one big image. An interesting way to think about it might be if you have a big mirror that's shiny all the way around. You've basically just got one giant mirror. If you have a mirror with a few individual shiny points on it, you're gathering a little bit of light at each of those points, and by synchronizing the light together, you're able to get some of the benefits of a very big mirror, or in this case, a very big telescope, by just putting little detectors all over the place. So that's something that the Very Large Array does. We have telescopes that can actually do this on a planet-wide basis. We synchronized telescopes on multiple different continents to take that famous picture of a black hole that everybody might remember from April of 2019.
Yes.
But it's an extremely difficult thing to do just mathematically and physically. So we're best at doing it at radio wavelengths, where the wavelengths are really long, which is why something like the Very Large Array takes such advantage of it.
Right, I see. And then the Very Large Array, those are all even on like railroad tracks or something, right? So you can move the like arrangement around.
They're arranged in a big Y, and you can make the configuration really big or really small. And that's effectively changing the size of, the giant mirror that you've got shiny points on. And that helps optimize it for different types of observations. But it's really great because there's a special instrument there that's just designed to kind of scoop up a telescope and put it on the railroad tracks and kind of truck it along to its new location.
So how is the movie Contact? Is it accurate? Is it just way off?
I thought it was pretty great. The book Contact is absolutely spectacular. I love the way that Carl Sagan writes, and it was kind of cool to see a story written by an astronomer about astronomy. A lot of times books about astronomy will be written by science reporters, especially if you're writing about the people and the human stories, which are wonderful. But Carl Sagan just got to bring such a unique perspective to Contact, and the movie made off of it kind of drew on some of his expertise. And they did a pretty good job of scientific accuracy. One of the only things that cracked me up in the movie, though, is actually shot at the Very Large Array in New Mexico, because there's a famous scene where Jodie Foster hears aliens, and you do not listen to radio telescope data. First of all, she would have been getting it through a computer, but sits up with these headphones on and hears aliens, and then has this mad dash back to the control room to look at the computer and look at the real data and see what's happening. And they film her driving through the real Very Large Array and driving through the telescopes and driving down the road and running up to the doors of the building and throwing them open and going like down the hall and up the stairs and down another hallway, and she hurls these doors open. All of that is filmed in New Mexico at the real Very Large Array. And then when she bursts through the doors, they're on a Hollywood set, because when the film crew got to the actual control room at New Mexico, they went, no, this isn't cool looking enough. This isn't high tech enough. We need to build a set, because it was all like really old computers and like tape drives and things. And we're working on, a government budget and a science funding budget that is not, extravagant. And the crew is just like, no, we need a slightly snazzier looking science room. So it's real right up until they get in there, and then it's a set. Yeah.
Right. Okay. No, that's good to know. That's interesting. So yeah, because I was like, she's like listening on the headphones and like hearing stuff. So you're not laying on your on your Mustang out in the field just listening on headphones.
No, we don't get to listen to the data on a Ford Thunderbird, sadly. No.
Right. Thunderbird. That's right.
They make a big point in the book that that's the car she drives, and for some reason that's a detail that I've always remembered.
Okay. So what would you say is the best film that has the best film representation of astronomers? Is it Contact, or is it something else?
I honestly think Contact. I can't blame them at all for having some fun and taking some cinematic license. Sure. We will in astronomy, in fact, some of the projects that I work on now deal with taking data that we gather that is light and translating it into sound. Sometimes it's for accessibility issues. The project I'm working on is looking at making data that visually impaired citizen scientists can use to help us study stars. People will sometimes translate data into sound just because it's an easy way to study it, but it never comes in that way. So I don't blame the movie for using that, just because it makes it a more immersive TV experience. And obviously, once we get into talking to aliens, we've a bit departed from the science that we know about so far, but I thought it was a nice depiction of what astronomy could be like and what these observatories were like. We got to visit the Very Large Array in Contact, and another observatory that features very prominently in Contact is also Arecibo. I'm not sure if you saw this in the news because it came out just in the past day or so, but the Arecibo radio telescope, it's this 1,000-foot dish in Puerto Rico, and it's being decommissioned. It had some support cables snap. It had been struggling for the past few years to keep itself supported through basically the funding that it needed to repair damage. And the National Science Foundation announced that it's being decommissioned and shut down. And it's just heartbreaking because it's got to be one of the more famous observatories that anybody's ever seen. Like if you just search Arecibo, Arecibo, it's the first picture that comes up. It played the GoldenEye, like villain lair in GoldenEye. It was in Contact. It's very recognizable, and it's been a science powerhouse for 50 years. So it's a very sad telescope to have to say goodbye to.
Yeah, man. So how does the I'm sure it's probably different depending on the circumstance, but how does the funding for these generally work? Who is paying for these?
It varies from observatory to observatory, but usually you'll have something like NASA or the National Science Foundation, or you'll have a consortium of research observatories, or sometimes like private foundations that fund scientific research that will get together and pool resources and combine money to build a telescope. And the way that sometimes works once a telescope is built is you might say have a telescope that's funded in part by the University of Hawaii. And once that's done, the University of Hawaii will say, we funded X percent of the project, so we get some defined percent of telescope time, which means that the scientists at Hawaii might still have to compete with each other or evaluate each other's proposals, but it gives you some access to that telescope. Others might be run through the National Science Foundation or some national organization or consortium of observatories, and then you can compete nationally for time or internationally for time. But they're usually built cooperatively because building even one of these telescopes is
sorry, we cut off there for a second. No, I got you though. Yeah, you were just saying building one of them is just like a huge endeavor, huh?
Yeah, absolutely.
Man, yeah. So you just need to build or just contribute 1/365th to a telescope, and then you get one night a year.
And your department might get one night a year, and then there will be 10 astronomers in the department. So you all get to compete for that one night.
Man, yeah, that's so crazy how limited it is. Is there plans to that one that you just announced was closing? Is there plans to replace it with something else?
I think that it's too early to say. I think every astronomer desperately hopes that they'll be able to replace it. But I mean, it was the largest radio telescope on the planet until I think 2016. And any attempt to replace it would be a just tremendous project. So it would be a huge undertaking. It's much harder to replace a telescope and build a new one from scratch than it would be to maintain an older one like this. And you might see descriptions saying, Arecibo's kind of old, but it was doing years and years of amazing science. And the fact that it was built in the 60s doesn't at all diminish that it was still an amazing instrument today. So it's really a shame that we have to sort of shut this one down rather than repair it, because building a brand new one is a much bigger effort. And it was already doing absolutely world-class science.
Right. Yeah. Dang, that's a bummer.
Yeah.
Can we talk about the telescope that's mounted on the back of the 747 plane?
Yes. This was one of my favorite adventures writing this book. But yeah.
It's awesome. It's so cool. I mean, do you have a photo of it or anything that we can maybe share on Instagram for people listening or something like that?
I do. Do you want me to send it to you or pull it up now or send it later?
Yeah, send it to me. And then for people listening, I'll post it on my Instagram and then they can go and check it out because it's so cool.
You'll know when it's posted. It's pretty distinctive looking. So there's a telescope named SOFIA, is what we all call it, which is an acronym, and it stands for the Stratospheric Observatory for Infrared Astronomy. We love our acronyms in astronomy, but it's a telescope that operates in the back of a specially modified Boeing 747. So the plane is designed to fly up into the stratosphere, so like 43,000, 45,000 feet, higher than most commercial aircrafts fly. Mm-hmm. And when it's up there, it then opens one of the rear doors, and there is a telescope inside the plane in a chamber that will observe right out the open back door. I got the chance to visit this telescope as part of my research for the Last Stargazers, and I spend an entire chapter talking about this weird telescope on a plane and some of its predecessors, because we've tried putting telescopes on planes before, and some of the other ways that we use to kind of toss telescopes up into the upper atmosphere. But it is such an adventure to fly on this telescope and just learn about how it works. It is so, so cool.
Mm-hmm. Yeah, because it's not even like it's an experimental aircraft, I guess, right? And you had to go through kind of a bunch of hoops to get on there.
I had to go through like a special safety training, and it's one of those safety trainings where they're very much like, we've never had an accident, please stay calm, but here's what you do if the plane is on fire. And you're like, right. Okay. But it was really, really fascinating. And an observatory like that runs with an entire crew, literally crew of people. SOFIA is operated by NASA, and they have specially trained pilots. They have people whose entire job is to just organize and run the entire crew of the observatory. There's people operating the plane, people operating the telescope, people operating the camera, people there for safety regulation. Like, it's really an amazing endeavor just to get this plane off the ground on a typical night. And then that it takes these amazingly sensitive observations is just great. But this is the whole advantage of SOFIA. It's flying very high into our atmosphere, which means it's flying above most of the water vapor in our atmosphere. And that water vapor blocks a lot of the light that is coming in from space from making it to the ground. And by flying above it, we can observe light that we normally wouldn't be able to see from a telescope just sitting on a mountaintop. So the scientific advantage of it is amazing, but it's an amazing project to actually get the telescope to where it needs to be. And it was so fascinating to have a front row seat to it.
Right. So just to kind of dive into that a bit deeper. So the reason it's important is so you can get above water vapor, you said?
Yep.
And so does that water vapor prevent like certain wavelengths of light to coming down?
Yeah, so the SOFIA specifically observes infrared light. So this is light that's a little too red for us to see with our eyes, and light that would normally bounce right off of the water vapor molecules. Okay. So the type of light that SOFIA studies is light that you really wouldn't get to observe in any real way from the ground, because all the water vapor in our atmosphere is blocking it from making it to us. But SOFIA kind of goes to the light and gets above the water vapor so that it can actually observe at wavelengths that we would normally never have access to.
Right. Yeah. That's so cool. It's like, well, it's blocking our way, so let's go on top of it.
Get above it.
Yeah.
Yep.
And then so when the telescope is in the plane. So, and then is it like looking through a window on the plane, or does a door open and it's actually like in the air? How does that work?
Door actually opens. So the plane is in its own, the telescope is in its own sealed off chamber in the back of the plane. Mm-hmm. And there's a door in that chamber that will actually open kind of like a garage door once the plane is in flight. And then the telescope is sitting inside the plane, but once the door is open, it's open and available to observe. And the whole plane is so well designed that door will open and close and you will never feel it.
That's amazing.
But suddenly you're on a plane with its door open.
Right, yeah. Oh, man, it's so cool. I love that. Okay, let's see. I have some other things I want to ask you about. Oh, with the 747, you would think that the turbulence from a plane, like just flying, would mess up the data, does it?
That's a great question. So the telescope is actually mounted on the world's largest ball bearing. If anybody needs a fun fact for parties, you now know where the world's largest ball bearing is. So the telescope is mounted on this thing. I think it's like almost 1.5 meters in diameter or something like that. And it floats on it. So the telescope stays perfectly steady, even if the plane bumps and jiggles a little bit around it. And you can hit turbulence that's so strong that it starts to threaten the image quality, but it would have to get pretty bad. It's actually really amazing how Sophia is able to observe even through the little bumps and shakes that we're used to, as anybody who's ever ridden on a plane has noticed. But that's enough to keep the image perfectly steady and clear.
Man, that alone is incredible. It's so cool that they've figured out how to do that and make it work. Okay, and then I want to ask about the, I believe it's the Reuben Observatory that's kind of doing the whole like survey type of thing, right?
Yes. Mm-hmm. So this is a new observatory that's being built right now in Chile. It's the Vera Reuben Observatory. So it was named after the woman who discovered dark matter. And it is a little bit different than the telescopes that we've been talking about, because we've been talking about telescopes that you apply for time on and you go to, and the telescope would sort of be handed over to you for a night to observe the list of objects or the pre-approved plan that you had. So the Reuben Observatory is going to follow a sort of preset plan right from the get-go. It's going to slowly survey back and forth and take pictures of a huge swath of the sky every night over and over again for 10 years. And that's going to be what it does, is just survey the night sky. And the amazing part of that is that it's going to effectively have built up a decade-long movie of the sky and anything that's changed in it. So it's just taking pictures over and over again. It sounds very simple. It's actually been an immense feat of engineering to build the telescope and of sort of data design and computer science to get it operating. But what it'll wind up spitting out is this amazing way of tracking anything that's changed. So an asteroid that's moving across the sky, we'll see. If a star gets brighter or dimmer, if a star explodes or disappears, we'll notice, because you'll see that tiny change in the night sky. And we've never had a data set like this before. So it'll be this amazing wealth of information on all these strange changing things in the sky that we can either study just using data from the Reuben Observatory, or that we can go follow up using another telescope. So it'll be this just font of data that we've never had before in the field.
Right. Yeah, that's so cool. So when you say it'll be 10 years, does it take 10 years to just kind of do one pass of the whole sky, or is it multiple?
It'll be hitting the whole sky once every few nights. If it just did the whole sky once, it would be done in 3 days. But it's doing that over and over and over again for 10 years. So that's part of the appeal. And I think that was just the experiment design, that the initial plan was, let's just take a decade and map the sky over and over and over and find everything that's changed. So just as one example, a great thing that this can be a tool for is finding a supernova. So a star that's died and created this amazing fireworks show and then left behind something like a black hole. A supernova in another galaxy is actually really hard to spot. It basically just shows up as this little like bing, like this little extra point of light that gets a little bit brighter. Mm-hmm. And normally we find about a few hundred of these maybe a year right now, because you have to be able to say, oh, there's a weird little point of light in that galaxy. Was it there before? So you need multiple observations of the same galaxy. And the Reuben Observatory is going to have multiple observations every few nights. So right now we find a few hundred supernovae in a year. That's how many that observatory is going to find in a night, one single night, because it's going to have such an amazing buildup of data and just say, oh, there's one. So we're honestly in the field getting ready for how we go from a time when we have a year to study those few hundred supernovae to when we get that many every night. It gives us an entirely different scale of data to work with. It becomes a really interesting computational problem, but it's super exciting because we'll have so many new discoveries to mess with.
Yeah, you guys are going to have a lot of work to do.
Oh yeah, we're ready.
Man, that's crazy. That's like how, I'm going through our old family photos and there's like 6 photos of my grandpa as a kid, but there's 6,000 of me. Like now we're getting to that point where you're going to have 6,000 or whatever, however infinity amount of photos of the sky. That's so cool.
Yeah.
So this thing will really just kind of act as like it's tracking the differences, like the changes in the sky. So it's going to be a good way to kind of discover things, like you said, right?
Yeah, exactly.
Okay. Makes sense. Thank you. I get it.
Yeah.
Okay. And then let's see. This is great. We've been going for almost an hour now. Let's talk about the telescope shooting story. Can you tell me that story?
Ah, yes. So people are listening going, the telescope shooting story, but
Right.
this is real. So when I interviewed all of my colleagues, I always asked them, what is your favorite astronomy story that you totally heard this one time at a conference that might be half true? And I was asking them, like, what's the weird version of this story? Like, you totally can't vouch for it, but it's a tale that's gotten told and retold and evolved in the field and become one of those like wacky legends that we tell in astronomy. And the most common answer by far was, do you have the one about the telescope that got shot? And I had a lot of fun piecing together the full true story of this, but there is in fact a telescope that got shot. It was in Texas, and it was at the time a fairly new telescope that had been built at this observatory. That was, people would call it the 107-inch telescope, because that 107-inch number referred to how wide the main telescope mirror was from end to end. With the telescope, everything very literally revolves around the size of the mirror, because the bigger the mirror is, the more light you can gather and the more powerful the telescope is. So you'll call something like, oh, that's the 3-meter telescope or the 1-meter telescope, or in this case, the 107-inch. And the story goes that an observatory employee at Texas was a little bit disgruntled and possibly on some substances he shouldn't have been on one evening, and became hell-bent one evening on destroying the 107-inch telescope. So he went storming in with a handgun, and fortunately nobody was hurt in this story, but he drew the gun and said, lower the telescope, because the telescope at the time was pointed up at the sky. So they lowered it as low as they could, listening to the guy with the gun, and he wanted to fire the gun down the sort of barrel of the telescope to shoot and destroy the primary mirror. And they lowered the telescope. He fired 6 shots into the mirror. But when you picture a telescope mirror, don't picture something like the mirror on your bathroom wall. A telescope mirror is a huge, heavy chunk of glass. It's made of the same stuff that like a Pyrex dish in your kitchen is made of, but it's about 1.5 feet thick. So shooting bullets into a 1.5 feet thick piece of Pyrex is kind of like throwing darts at a dartboard. And the bullets just kind of went thunk and stuck and embedded in the glass. So he was deeply underwhelmed with this result. He started to try and go at the mirror with a hammer. At some point, he was subdued. The sheriff was called and he was led away. But the damage to the mirror was amazingly really tiny. They were able to just dig out the bullets and then paint over the holes and keep observing. And the joke was, well, there's a couple little empty bits in the mirror now. So maybe instead of a 107-inch mirror, it's like a 106-inch mirror, but it's probably fine. The only problem was that word got out into the community that the telescope had gotten shot. And by the time the story had circulated, there was this fear of like, my God, it's been destroyed. It had bullets shot into it. Isn't the telescope completely shattered and done for? And the director of the observatory had to put out this announcement to the community. And usually when people put out community announcements, it was things like, we found a new supernova in this galaxy, someone should go follow it up. Or we saw this star do something interesting, someone should check it out. And this announcement comes out reassuring people, yeah, we're fine. The harm from the bullets was extraordinarily small. The mirror will continue working flawlessly, and we're still using it now. So it absolutely became this legend of the telescope that got shot. And chapter 5 of the Last Stargazers is now titled The Harm from the Bullets Was Extraordinarily Small, because it's got to be one of the best astronomy announcements that's ever gotten circulated.
Yeah, that's so crazy that it was just able to, it just, took it down an inch basically. Like it's still fine, really.
They're still there. The mirrors get taken down every few years to be sort of recoated. We'll coat our telescope mirrors. They're big chunks of glass, but we coat them with a thin layer of aluminum so that they're nice and reflective. And every few years, you'll take a mirror out to sort of clean it and recoat the aluminum. And when you do, you can see the bullet holes are still there.
Man, that's crazy.
Yeah.
That's like they have it in Disneyland at the Haunted Mansion. Some kid took a BB gun and shot a window, and it's like super hard for them to replace it for some reason. So they just stuck like a spider web over it or a sticker spider on top of it, and it's fine.
Yeah, it's still working. It's good.
Right. Yeah. Man, I love that story. That's so fun. So, and that's what your book is, right? Like it's just all these like fun stories that really I would have no idea about or exist. So it's fun. I'm glad you wrote the book. So thank you.
It's funny because I got the idea for the book by thinking about the stories that astronomers tell each other. That when we're sitting around at a conference or we're killing time at a night at a telescope because it's cloudy, what do we tell each other, and what kind of stories do we use to communicate what it's like to do our job? And I realized that using those stories to tell readers about our job was a really great way to do it, because for one, it puts a human face on astronomy. Astronomy can feel really remote and really inaccessible, and I like the reminder in any field that science is done by people and done by humans who are piloting our cars up these roads without our lights on and sleeping in these dorm rooms and then hoping that the telescope doesn't get shot, and sort of having these weird, wacky adventures as we do our research. And you also get to learn science as you do tell these stories, because we've talked tonight about the light that makes it down to the ground versus the light that is above, that gets blocked by water vapor. So we need to fly a plane up to get to it. We talked about how important a big mirror is to a telescope, or how the different wavelengths of light work. So you can use the storytelling to kind of make the science accessible and to remind people that there's human stories behind it, but you get the science along the way. So using those stories to kind of follow the framework and the story of the book as a whole, which is looking at what our jobs are like, the adventures we have, and how our jobs are changing, just seems like a really good way to share this science with an audience.
Mm-hmm. Yeah, no, it's awesome. And like, being someone who's not an astronomer or a scientist or anything, I loved it. It's awesome. So you don't need to be in the field to enjoy it, which is nice.
No, thank you so much. It was a really fun book to write.
So let's mention the book for people listening. The full title is The Last Stargazers, the enduring story of astronomy's vanishing explorers. Anywhere we should send people specific to get that?
You should buy it from whichever bookstore you want to support. So you can find links to it on, Amazon and Barnes and Noble. I can also highly recommend IndieBound, because it lets you purchase books from your favorite local independent bookstore. And you can purchase it in hardcover, the beautiful hardcover with the star-studded inner jacket, or ebook form. And it's also available as an audiobook.
Oh, nice. Cool. Did you do the audiobook?
I didn't. There was a wonderful narrator named Janet Metzger who did a spectacular job with the audiobook.
Nice.
Yeah.
Okay. Well, I'll have links for on IndieBound, Amazon, whatever, for people to grab your book in the description. Go ahead.
If people want to learn more about it too, the book has a website, so thelaststargazers.com, or you can follow me on Twitter. My username is EMSQUE, EMSK, and the Last Stargazers hashtag is a good way to keep up with the latest news on the book.
Okay, perfect. Okay, I have all that stuff written. So yeah, I'll have links for people listening to click on that stuff easy too, so they can find all that and find you. So this was great. I love this. Is there anything that we missed, or that you'd like to portray, or some common misconceptions or anything?
The one question that people tend to ask is they're curious about the title, because the title, The Last Stargazer, sounds really sad, and it sounds like it's going to be this heartbreaking, depressing book about how astronomy is being ruined. Right. And that's not the meaning of the title, although the title is a little bit of a challenge. It's partly a reference to the way that technology is changing astronomy and the roles that astronomers play in our own observations, because we used to be at the telescope. We used to be in the telescope with these glass plates, like riding along during the night. And now we can operate telescopes from another room, from another building. I can now operate some telescopes using software on my laptop just from my office. That capability has also become extraordinarily important in the middle of a pandemic, being able to run telescopes remotely however we can. But it's really changed the stories that we tell about how we observe. And I wanted to write a book that saved those stories. And then the challenge side of The Last Stargazers is that I think people see that and go, well, wait a minute, I stargaze, or I have friends who stargaze, and plenty of people still stargaze every day, maybe for their jobs as professional astronomers, or maybe just for the pleasure of it. And I think recognizing and using that passion and love for stargazing and love for science is really valuable. There's a lot that technology can give us, but we shouldn't be the last stargazers, because the human curiosity is always going to help drive what we do in science. No matter how much the technology helps us, our ability to kind of be curious and ask questions about the universe and decide to answer them is such an important part of science.
Mm-hmm. Yeah, totally. So what do you kind of see as what's the future of astronomy look like?
It's an interesting question because the future of astronomy really depends on how much support we have for scientific research, how much we're able to keep building new telescopes and bigger telescopes and more powerful telescopes, and how we can support the people who are in astronomy or tomorrow's stargazers who want to enter the field by making sure that we have science funding and research funding, by making sure that there's jobs in the field and that there's the resources that we need. So I hope that the future of astronomy is heaps of wonderful, powerful telescopes and tons of people who are already so interested in space and love science that are able to participate in answering all the questions that those telescopes sort of open up for us. So that's my hope for the future of astronomy. And my hope is that a book like The Last Stargazers helps remind people of why science is so exciting, why astronomy is so exciting, and who the people who do it are, so that we can keep supporting it as we go forward.
Nice. I love it. Cool. Well, thank you so much, Emily, for being on here and sharing this stuff. Really appreciate it. Thank you.
Thanks so much for having me.